Welcome to Software Architecture System Security. This is Lecture 9, Professor T. Freed Muhammad. Software architecture is the fundamental structure of a software system defining how components interact and work together. To fulfill the system's requirements, it serves as a blueprint that outlines the system's design, including the organization of components, their interfaces, and the relationships between them. So let's get started in this area. The definition of security is protecting data and information from unauthorized access. The importance is ensuring system integrity and availability happens. A well-designed software architecture ensures that the system is robust, scalable, and maintainable, enabling it to adapt to changing requirements and technologies over time. It provides a framework for developers to build upon, ensuring consistency and coherence across the system. Before I jump in depth on confidentiality, integrity, and availability, the CIA triad, I would like to set a context. The system security is a critical aspect of software architecture, focusing on protecting the system from unauthorized access, data breaches, and other security threats. It involves implementing security measures at various levels of the architecture, including authentication, authorization, encryption, and secure communication protocols. By integrating security into software architecture from the outmost, organizations can mitigate risks and ensure that their systems are resilient against attacks. This proactive approach to security helps to safeguard sensitive data, maintain user trust, and comply with regulatory requirements. So the characteristics of security comes in handy when we look at confidentiality. That means protecting data from unauthorized access. Integrity means preventing unauthorized manipulation of the data. And availability, ensuring system availability for legitimate use when we are dealing with any data at our hand. The security properties are authentication, non-repudiation, and authorization. Authentication means verifying identities of users and systems. Non-repudiation means ensuring actions cannot be denied. And authorization means granting access based on privileges. Let's look into this in a little bit more depth. Authentication is a cornerstone of secure software architecture, serving as the first line of defense against unauthorized access. It is the process of verifying the identity of users, devices, or other entities attempting to access the system. In software architecture, authentication mechanisms can include passwords, biometrics, tokens, and certificates, often implemented through protocols such as OAuth, OpenID, or multi-factor authentication, also known as MFA. By enforcing robust authentication methods, software architects ensure that only legitimate users can access sensitive data and system functionalities, thereby protecting the integrity and confidentiality of the system. Effective authentication also supports accountability, enabling the tracking of user activities and enhancing overall system security. Non-repudiation is a critical security principle in software architecture that ensures actions or agreements cannot be denied by the entities involved. It provides irrefutable proof of the origin and integrity of data, transactions, or communications, preventing participants from falsely denying their involvement. Non-repudiation is typically achieved through digital signatures, timestamps, and secure logging mechanisms, which create an audit trail that can be verified by third parties. By implementing non-repudiation, software architects enhance accountability and trust within the system, making it essential for legal compliance, dispute resolution, and maintaining the integrity of business process. Authorization is a fundamental security concept in software architecture that determines the access rights and permissions of authenticated users or entities within the system. It ensures that users can only access resources or perform actions that they are explicitly permitted to. Based on their roles, attributes, and security policies, authorization mechanisms such as role-based access control or RBAC, attribute-based access control or ABAC, and access control list ACLs are implemented to enforce these permissions. By carefully managing authorization, software architects protect sensitive data and system functionalities from unauthorized access, enhancing security, compliance, and operational integrity. Effective authorization also supports the principle of least privilege, minimizing the risk of internal and external security breaches. Security general scenario: the components are source, stimulus, artifact, environment, response measure. The example is unauthorized access of a university grading system. We will actually look at a detailed use case of a university management system and how software architecture's implementation of security controls work on top of that. Security tactics overview: categories: detect, resist, react, recover. The goals are protecting systems through layered security tactics. Let's look into this with an example. Security tactics in software architecture encompass a range of strategies and techniques designed to protect systems from threats and vulnerabilities. These tactics are implemented at various stages on the software development lifecycle to ensure robust and comprehensive security measures. Key security tactics include threat modeling, which identifies and mitigates potential security risks, secure coding practices, which prevent vulnerabilities such as injection attacks and buffer overflows, and regular security audits and prevention testing to uncover and address weaknesses. Additionally, tactics like encryption for data at rest and in transit, secure authentication and authorization mechanisms, and the principle of least privilege are employed to safeguard data and control access. By integrating these tactics, software architects build resilient systems that can withstand and recover from security breaches, maintaining the confidentiality, integrity, and availability of the information as we discussed earlier. Detecting attacks: detect intrusion using the signature and patterns. Detect service denial or DDoS, dynamic denial of service, comparing traffic to known denial of service attack profiles. Verify message integrity using checksums and hash values. Let's look into this with an example. Detecting attacks is a crucial aspect of maintaining the security and integrity of software system. It involves implementing monitoring and detection mechanisms to identify and respond to potential security threats in real time. Techniques such as intrusion detection systems or IDS, which monitor network traffic and system activities for suspicious patterns in security information, and event management or SIEM systems, which aggregate and analyze security related data from various sources, are essential for early threat detection. Additionally, machine learning algorithms, which come in handy if you are working with the artificial intelligence incorporation in a software architecture. That is where machine learning algorithms can be very helpful for you. So regular security audits, log analysis, and user behavior analytics further enhance the ability to detect and mitigate attacks, and ensuring the systems remain secure and resilient against evolving threats. Detect message delay. Monitoring message delivery times is a significant aspect as well. The importance of detecting message delays is early detection to prevent further damage. So in case if the messages are coming in terms of a delay, that is also something that we should be mindful, because the data leak detection comes when the message comes in terms of a delayed aspect. Monitoring the dark web and surface web for compromised credentials is essential. Data leak detection tools scan for listing matching predetermined keywords related to internal credentials, because the delay in the message can leak the actual information out, and that can go into the dark web for sale. So we have to be mindful in that aspect. Resisting attacks, it means identify actors, authenticate actors, and authorize actors and how they are performing. Let's look into this with one example. Incorporating resilience against attacks into software architecture involves designing systems with security as a foundational principle. This approach includes implementing robust authentication and authorization mechanisms to control access, employing encryption to protect data at rest and in transit, and adopting secure coding practices to minimize vulnerabilities. Additionally, architects should integrate continuous monitoring and automated threat detection systems to identify and respond to attacks in real time. By embracing principles such as least privilege and defense in depth, and regularly conducting security assessments and penetration testing, the architecture can effectively resist and mitigate the impact of cyber attacks, ensuring the system's integrity, confidentiality, and availability. Limit access and exposure, minimizing attack surface. Encrypt data, protecting data through encryption. Separate entities using physical or virtual separation whenever we are designing the architecture. An example comes in terms of revoking access, lock the computers, and inform actors. So this flow goes: limiting access during suspected attacks, preventing access after repeated failed attempts, and notifying personnel of potential threats. Audit and logging, keeping records of user and system actions. That goes to recovery strategies. That means restoring data and services after an attack. Design checklists for security, allocation of responsibilities such as assigning security tasks. Coordination model utilization means ensuring secure communication and coordination. The data model goes managing data sensitivity and access rights. Design checklists, that means resource management, binding time, and choice of technology. So let's look into this with an example. While creating a software architecture design checklist, resource management is a critical component that ensures the efficient utilization of system resources. This includes assessing and allocating computational resources such as CPU, memory, and storage to meet performance requirements. Effective resource management involves implementing scalability solutions such as load balancing and auto-scaling to handle varying user loads and ensure optimal performance under different conditions. Additionally, the checklist should include strategies for resource monitoring and optimization, such as using profile tools to identify bottlenecks and inefficiencies. By incorporating these practices, architects can design systems that are not only performant but also cost-effective and resilient to changes in demand. Binding time is another crucial consideration in the software architecture design checklist, as it determines when and how decisions about system behavior are made. Early binding, where decisions are made at compile time, can enhance performance and security but may limit flexibility. Late binding, on the other hand, allows for greater adaptability and easier updates, but can introduce complexity and potential security risks. The choice of binding time should align with the system's requirements for flexibility, maintainability, and performance. Architects must evaluate the trade offs and select the appropriate binding strategies for different components of the system, ensuring that the architecture remains robust and adaptable for future changes. The choice of technology is a foundational aspect of the software architecture design checklist as it directly impacts the system's capabilities, performance, and scalability. Selecting the right programming language, frameworks, and tools is essential for meeting the project's requirements and ensuring long-term maintainability. The checklist should include an assessment of technology trends, compatibility with existing systems, and skill set of the development team. Additionally, considering the technology support for security, scalability, and integration with other services is crucial. By carefully evaluating and selecting technologies that align with the project's goal and constraints, architects can build a robust and future proof software architecture that meets both current and future needs. Applying security to university management system. So, overview of the university management system, as we have been discussing in this software architecture discussions for quite a while, that it deals with professors, students, administration, and other facilities management within the university system. Applying security principles to protect sensitive data and services, as mentioned earlier, to make sure that we are remaining within the CIA triad: confidentiality, integrity, and availability. So we have to be mindful when we are working with these things. The components in a UMS or University Management System security scenario has source, stimulus, and artifact. Source is students, faculty, administrative staff, external attackers, as just mentioned, where external attackers are the one who are to come and steal the details. Stimulus is unauthorized access to grades, personal information, and financial data associated to university and any stakeholders, whether direct or indirect. Artifacts are student records, grade databases, and financial systems. Confidentiality in university management system, protecting students' data, ensuring only authorized personnel can access student records. And encryption comes handy where using encryption for data at rest and transit is helpful. Access control is implementing role-based access control or RBAC strategies, and let's look into that with an example of Department of Computer Science, for example. Implementing role-based access control, as discussed earlier, within the Department of Computer Science, if we take that as an example, is essential for establishing confidentiality in software architecture design. So when we are designing our software architecture, we have to keep in mind that RBAC ensures that access to sensitive data and the system functionalities is restricted based on the roles and responsibilities of individuals within the department. By defining roles such as faculty, research assistants, administrative staff, and students, the department can enforce access controls that limit data exposure to only those who need it for their specific tasks. This approach helps protect intellectual property, research data, and student information from unauthorized access, thereby maintaining the integrity and confidentiality of the department's digital assets. In the context of software architecture design, RBAC enhances confidentiality by ensuring the developers, testers, and other stakeholders have access only to the components and data relevant to their roles. This principle of least privilege minimizes the risk of data breaches and unintentional data leaks. By integrating RBAC into the architecture, the department can also facilitate easier auditing and monitoring of access, enabling quick detection and response to any unauthorized activities. This proactive approach to security not only protects the department's assets but also fosters a culture of accountability and trust among its members. Integrity, as mentioned earlier, has data accuracy, audit trails, and checksums and hashes, whereas data accuracy, as mentioned earlier, ensuring grades and records are not tampered with. Audit trails are needed to be maintained. It allows us maintaining logs of changes to critical data, which is done legitimately. The checksums and hashes verifying data integrity during transmission and storage is also a paramount. Availability in the university management system, system uptime, redundancy, denial of service protection. In system uptime, ensuring the university management system is available during peak times, such as registration periods. Redundancy means implementing backup systems and failover mechanism. If one app has gone down, the second app should take on by helping the students carry on their day. Denial of service protection, detecting and mitigating the denial of service attacks. Detecting attacks in the university management systems, as mentioned earlier, we look at intrusion detection systems, which is IDS. We also look at anomaly detection and real-time alerts. I suggest you to conduct a research on these topics for your learning. Resisting attacks, as mentioned earlier, has MFA implementation, firewalls, and VPN implementation, as well as regular security audits. So you can look into these as per your availability of the studies that you're conducting in systems architecture or software architecture. And we all go through these things in our daily life when we use banks and all that jazz, as well as university management systems. Reacting to the attacks in a university management system, incident response plan is to be establishing protocols for responding to security breaches, isolation of affected systems, containing threats to prevent further damage. Communication is informing stakeholders, students, faculty about security incidents. Data backup and restoration, ensuring data can be recovered after an attack. Post-incident analysis, that means investigating the cause and impact of security breaches. Improvement measures allows us to implement additional security controls based on lessons learned. University Management System Security Checklist has access control, where we define the roles and permissions for system users. Data protection comes handy by implementing encryption and secure data handling practices. Monitoring and logging helps us establishing systems for tracking and analyzing security events. Regular updates ensure software and security protocols are up to date. I wish you best of health, happy learning, and carry on working with software architecture in depth.